Hi, Amanda. How are you?
Good,
We
how
are
are
ready this
you?
time. Sorry for the problem in the morning.
No, no, not at all. Are you ready to get started or are
Yeah.
you all okay,
No,
great.
we are ready. We are ready.
Perfect. So this is the last tutorial of the day. And everyone here probably knows everyone presenting from the earlier tutorial, but I will give a very brief introduction. DK Panda is a professor and University Distinguished Scholar of Computer Science and Engineering at Ohio State. He has published over 500 papers spanning topics such as HPC, big data, and data science. Dr. Hari Subramani is an assistant professor at Ohio State, researching topics spanning high performance computing, architecture, big data, deep learning, and cloud computing. Dr. Amir Shafi is a research scientist at Ohio State, researching topics spanning big data, machine learning, and deep learning, and HPC. And Naris Al Nassan is a graduate research associate at the Network Based Computing Lab in Columbus. He is pursuing a PhD in CS, and his research interests lie at the intersection of deep learning and HPC. And they are going to give the tutorial on principles and practice of scalable and distributed deep neural networks training and inference. I will post a link to the Slack channel for this in chat, and you all can get started whenever you're ready.
Okay. So, Amanda, thanks a lot. And good afternoon, all of you. I know you have been attending the conference almost 3 days, so this is the last event. Um, so, as you can see here, we have the a copy of the slides. You should be able to download from this site, and might be Amir or Nauras. So you can post it on the chat also. Amanda will be posting on the Slack. So we'll be monitoring. Please post questions on the chat or on the Slack, and we'll be keep going. So as you know, I mean, we are in a very exciting field of the field of AI, and especially in the AI, as you know, like people are trying to do training, inference, and this is where like a lot of actions lies with respect to the very latest systems. What is the role of the networking? What are the kind of the frameworks? So that's what we'll be trying to go over it. So this will be the outline. We'll start with a very high level introduction just to warm you up, saying what is the past, present, and future of AI. Go over a little bit about machine learning and deep learning, deep neural networks concepts. There are diverse applications of deep learning. And then we'll go into a little bit of the deep learning frameworks themselves, because this is where most of the AI users interact, like PyTorch, distributed PyTorch, DeepSpeed, etc. And then we'll go into some basic concepts of deep neural network training, like how do you actually utilize the GPUs, what are the basic concepts, what you should be looking for when in the scaling. And then you might have heard of like a different kinds of parallel training, like the simpler one is a data parallel training. So we'll go into that distributed data parallel training. And then we'll also do some kind of hands-on exercise. Since the time is short, we may not be able to actually provide all of you accounts. In fact, we had planned for that, but we may not be able to fit everything. But what we'll do is like an hours will be driving the hands-on exercise, and then you can carry out similar kind of things on your systems. And then what we'll do is we'll bring the latest trends in the HPC architecture, bringing the very latest on the high performance interconnect, and then try to see how these fields are being fused together in the current and upcoming systems. And then we'll go into some advanced distributed training. These are some model parallelism, spatial parallelism, those parallelism, and we'll take a look at some of the numbers. And then we'll come back to inference. So, of course, a lot of work has happened in the past about training. And once the models are there, people are focusing on the training. That's what we'll take sorry, inferencing. And then towards the end, we'll just highlight some of the open issues and challenges and conclude. So, as many of you might be knowing, just to put the terminologies correctly, many people use this word of AI, machine learning, deep learning. Sometimes they interchange. So, I just want to have the set uh, clear. So, the field of AI, this is what you see on the bigger box, is the very big field. There are so many things happening there. What we'll be trying to focus within that field is the machine learning. And then within that machine learning, even there is a smaller subset, which is the deep learning. Okay, so this is what we'll be trying to cover. And and what you will take a look, the very broad difference between machine learning and deep learning can be illustrated by these two figures. So machine learning has been there in the field for many years. So if I have a set of inputs, then the standard practice has been to do some feature extraction with the help of some person, then do some kind of a classification, and then come up with that model. And then based on that model, if I have a new input, it is trying to see, okay, what it does based on that model. The deep learning basically tries to fuse these two steps and try to give the entire responsibility to the computer itself. Okay. So we are trying to fuse. So given a set of data, we are trying to build the model completely. The computer is trying to build the model. And then once the model is there, when the new input is coming, the new input can actually be uh, I mean, this model, the new input can be fed to this model. That is the kind of the inferencing we'll be talking about, and then see whether the new data is able to predict the correct things. Because this is a very high level, like a 100,000 feet level. Of course, in this tutorial, we'll go into more details as we go down. Now, if you take a look at the history, I mean, the field of AI has been there. Even if you go back, like here we are talking about 1800s. People were talking about like a basic concepts, mathematical concepts, linear regression, PCA, Turing machine. Even at 1947, 43, almost like a 80 years back, people started even talking about electronic brain. Um, and then over the years, these things have been continuously evolving in this field. And as you can see, bottom, these are all the big heroes in this field. Now, what happened in this during this time period, like in 1960 to 70, it was called as a golden age because a lot of new ideas came up here during this time. Okay, a lot of theory, a lot of kind of algorithms got developed. But then what happened? This is called like a dark age. So that means even those ideas were there, but people were not able to validate or prove or anything. Okay, the main reason that that computing capability during that time was not sufficient to understand the field itself. But then recently, as many of you know, we're in an exciting field. All these things have taken a very rapid progress. And that has happened not only because of the availability of the new CPUs, GPUs, all kinds of new networks, also availability of a lot of data sets. And then that is helping people to actually try out many of these, and then we can actually make faster progress. So this is what is shown. Like if you just take a little bit, this is the data. We took it from not very far, like a 1.5 years back, November 22. I know most of you are familiar with top 500. So here you will see these data are mostly dominated by GPUs. Okay. And these are like the top 500 systems. And in fact, that is still continuing the trend. So, and continuously also larger and larger systems are being deployed over the years. But it's not just the computing matters, but the data sets also matter. Okay, so this is what started with 2014, almost like 10 years back. This ImageNet challenge started, and then after that, this Kaggle community also started the Kaggle competitions. So through these competitions, a lot of data sets and all were made public. And that actually helped a lot of researchers, practitioners to jump in and play with those data sets together with the computing environment. And then they try to see whether they can come up with better solutions or better algorithms. So here it shows a very high level view of just to get a feel. There's a lot of um, such market predictions are coming here. We are just using uh, two of these as shown here below. So it is trying to show like how there has been an exponential increase in the market. We are here just in 2025. In another year, people are predicting like it will go from almost like a $28 billion to 32 billion kind of things. And where people are trying to expect this kind of a revenue. So these are like a top 10 use cases. The indicated as in the same article. Um, these are the top 10s like a contract analysis, object detection classification, identification, geospatial images, automatic automated geospatial feature detection, text query of images, content distribution, predictive maintenance. This maintenance could be for cars, for trucks, for airplanes, all kinds of different units. And medical field, that is also getting a lot of traction with respect to AI, and these are the like the image recognition, classification, and tagging. These are like all the different content which is being created all over the world through social media and all. And of course, the always the number one becomes the stock market, like the algorithm trading strategy, performance improvement, because those people have deep pockets. They always want to invest on these and try to compete with each other. Now, if you take a look at the very start with the very machine learning, many of you must be knowing these terminologies. So these are like the standard three kind of machine learning, supervised learning. This is where the machine learning field started. Like we have some set of data, then we come up with our algorithm, but also a human is involved in coming up with that algorithm based on the data, do the processing, and once the model is there, then of course the new input, again you can see okay what classification, like in what class it belongs to. Then of course people move to unsupervised learning. So here the idea is that try to eliminate the human in the loop. It is automatically like based on the interpretation, the processing, and the algorithm. It itself can build up the model, and the inferencing remains the same. And of course, there are a lot of progress has happened in recent years in terms of reinforcement learning. So it is not only like a you are trying to develop this model, but the model is also trying to the agent is trying to provide some kind of a feedback, and based on that, you are trying to keep on doing the reinforcement and have better and better models. So that is kind of a very high level with the machine learning, but let's go into a little bit more deeper on the deep learning. This is how I'm sure many of you would have seen in some papers and all what is called deep neural network. And in that deep neural network, it is typically called like a input layer. There are like in this case, it is a three-layer deep neural network example. And this is what will be giving a lot of focus. How do you train such things? So you start with a clean slate. You may need to define your number of layers, number of nodes in every layer, and then these weights. And based on all these inputs, we go through training, and gradually these things get strengthened. Okay. Is there a question here on the chat? I think. Let me see. No, okay. So the question is for the lab session, do we need to download any data set? No, no. We are not doing anything. So just refer to like we'll be trying to do kind of a demo kind of things for the lab. Thanks. So if you take a look at the previous picture and then let's take a look at this kind of our human brain. I'm sure this left hand side, um, you might have seen this. You have learned this from some biology 101 classes in your high school. Okay. So our brain is full of billions of such neurons, and typically the neuron kind of has a nucleus. There are some dendrites, and based on the activities, there is an action which carries the impulse from the left hand side to the right hand side. So like this, all these neurons are all working together in our brain to uh, make decision. All our human brain is working like that. So the right hand side is actually a mathematical representation of that neuron. So when people started with these concepts of electronic brain and that idea has been continuously being enhanced, this is what you will be seeing on the right hand side. So we are calling this like the cell body, just like the left hand side. You will be seeing these are like the synapses, the dendrites, having some different kinds of weights, and then the cell body performs some function, and based on that, it also generates an output. And then this is how the billions of neurons again can be connected in all together to come up with the complete solution. So then, as I indicated earlier, um, there are two basically key phases of the deep learning. We'll be covering both of these. One is called the training, and the other one is inferencing. So this is where, especially in the deep learning, the first thing is you need huge amount of data. That is the first thing you need to you need to be make sure you have data, and then we start with this kind of a model. How do we saw what we saw in the clean model, and then that clean model, as we operate on those data, there are a lot of these forward pass, backward passes. Okay, And then through this forward pass, backward passes, we also try to see whether we are capturing that model in a much more accurate manner. There will be a lot of errors, and that's what happens. There is a backward pass. We take these errors, and then by taking that error into account, we actually evolve this, and then come up with a model, and then you can actually then take the new image or something, and then trying to go through the inference. Okay, that's what it's trying to show. And then if you, let's say we are trying to train these with human faces, uh, and if you bring a new human face image, and if it is detects properly, then that is model is good. If not, it's not correct. and and this is no different than how actually human beings, if you think of like how a baby develops over the years, like once a child is born, you will see the, let's say take an example of a fire. A child doesn't know what fire means. In the very beginning, you might want to see the child will put his or her hand or finger in the fire, but gets a response. And then over the years, then the child feels that, oh, this is the fire. I should not be putting my hand. So think of like that is what training is happening in our human brain. Same thing happens like whether you consider driving or swimming or learning a class, learning any other kind of a spelling, language. You name anything, we human being are continuously learning. Okay, and that's what exactly happens also here when we say deep learning. Exactly the same procedure, we are trying to do it by computer. And once the training happens, then when we have a new situation, so for example the driving, if you might have driven in some areas, you have learned the basic concepts, you might be able to drive well, but the question is, okay, can you drive at a new place or a new city? Okay, so if you can drive well, that means you have been trained well. If not, you may need to still improve. So that is the whole thing we are talking. And especially the training side, the question is like if you have huge kind of data sets, um, you need huge amount of systems. This is where the parallel training comes into picture. You cannot do it in a one node or one GPU. You need thousands of these GPUs, and that's what we'll focus on. Now, gradually what is happening, the same thing is also happening to inference. Inference individually, it may not take a lot of time. You can do it in the CPU or a GPU. But think of like the servers when, let's say, Chat GPT, at any time, millions of queries are coming to the OpenAI servers or wherever the servers are hosted. So that is also becoming very important. How do we really give lower latency to each one of these inference? So that is where also the parallel distributed training is being used. So there is a nice um, thing here. Let me go to this actually, open up this link. Just give me a point. Uh, TensorFlow. Let me share this page. Give me a. Can you see my screen, TensorFlow?
No, Dr. Panda, we see the presentation.
What happened? Give me 1 minute. How about now?
Yes, we can see it now.
Yes. Okay. So here it is a very nice tool. If you are a kind of an educator or a teacher, or if you just also want to learn yourself, this is a very nice tool here, which is like TensorFlow. As you can see, playground.tensorflow.org. So if you take a look at here, so let's say the left hand side is like the different data sets. I want to build a model. I can actually add a layer here, even add a, for any of the layer, I can add neurons. I can actually select some data. So let's say I select these data sets, um, or even let's take this one. I think it has the red and blue kind of things, and we want to train it. And then if I click here on the top, um, here you will see how the training is taking place. You can see these different weights and all. You can click at any of the link and seeing these weights are being improved over a period of time. And the right hand side, you can see actually how it got finally it clustered into two different regions. We can also try to do for a different data sets similar kind of things. We can see like a uh, orange and blue. And then it is also giving a lot of these things we'll be trying to learn, like a learning rate, activation, regularization. We can introduce noise here, different kinds of batch sizes. So these are the kind of the terminologies we need for training. And that's what actually we'll go down and take a look at it. Now, once we have the training, then the question is inferencing. There is also a very nice tool here. Let me go there. Um, that is in the slide. You can also do. I'll just share that. Um, it is okay. Let me share this. You can see my screen. So it is a Restaurant 50 trained on ImageNet. It is trying to load the model. So let's say you have this previous example, like based on the data sets, you have trained the model. And now once you load the model, this is loading the model to my like a laptop, and it can actually utilize the CPU or GPU to do the inferencing here. Let's just give you 1 minute to, it is trying to load the model. Hmm. I think
So
it's not.
yeah, it takes around 1 minute to load. Do you want me to
Okay.
share my screen, Dr. Panda? I
Yeah,
have
yeah,
it
yeah. Go
loaded on
ahead.
my
Go ahead.
end.
If you have loaded,
Okay.
go ahead. Yeah, go ahead. I'll say stop
So
sharing.
yeah, I'll just share the screen.
Yeah.
Uh,
So if you see here, so let's say you have trained the model. So let's take an image like a bird. So we have that model, and now if you give a new input, in this case, it is trying to see, okay, what kind of bird it is. Like in this case, it is saying hummingbird. And top, if you see, the back end is actually it is on the GPU. On the GPU of your laptop, you can also do a CPU. It is also trying to say on the right hand side top inference time. Okay, 233 millisecond is taking. So let's just select another one. Might be bridge. Select bridge.
yeah.
Bridge. Yeah. So here you will see we have those. This is like from a bridge, might be the San Francisco, the Golden Gate Bridge. Many of you might have seen, but on the right hand side is not able to detect it properly or inference properly. It says like it looks like harp. The system, because of those strings, it it is detecting it as a harp or a then suspension bridge with a 44%. So this is trying to give an example saying, look, the training might not have been done properly. Okay. So like this, you see applications are popping up in all different domains, and in fact many of them are actually helping a lot of people. I don't know, many of you know, like say, in the laptop, in your iPhone, you can actually download a lot of these apps for identifying birds, identifying plants, insects, flowers, vegetables. All these kind of common things are coming. Of course, these are common for us to learn. Very simple, like many weekends my wife and I, we go to the parks, and anytime like there is a new plant, if we don't know, just my wife just brings the iPhone, and then she's able to exactly find it out what that plant has, and you get all the details. So this kind of think of like AI is helping us human beings in this example to also to learn, also to get educated. But the same ideas you can take, like a pathologist might be using Those are the kind of things we'll be seeing more and more complex things. Okay. So with this, let's go into the slide deck. Again, I'll share. Um, okay. So this is the example we saw, but there are many more examples. If we take a look like a credit card fraud detection, this is a very common example. Many of you might have experienced when you do some kind of credit card transaction, you may get a note from your bank or something saying it has been declined or it couldn't go through. Um, and underlying the scheme, there is actually there is a model and there is a prediction based on, let's say, for me, the spending patterns. I'm in Columbus, Ohio. Most of my transactions are happening in Columbus. All of a sudden, if I go to Germany and start using there, it may detect saying that it is unauthorized. But over the years, it is actually is very improved. Means many of you might have seen like 20 years back when you go international travel, you may need to tell your bank saying, look, I'll be using my card in such and such place. So they put that information, but you don't have to do that today because of the databases. A lot of these things are being connected together. So if I'm going to Germany, I am sure like I have purchased a ticket and that ticket or as a hotel, that information is already available to some of the banks on the based on my credit card. I have done already a booking. So then it actually takes that information into the model. And then I don't get this kind of unauthorized or a credit card fraud detection things. So the list can go on, like a lot of scientific simulations are happening now, even very simple, like you can have like a Google Translate. You are going in a foreign country or trying to take a look at the look at some of the things you are trying to buy. This is a very nice example you might have seen over the years. Think of like, let's say any, let's say Van Gogh. Van Gogh has a style, so the question is like, can the machine actually learn Van Gogh styles? And if we give a doodle, can the machine produce kind of an image? Okay. Of course, I mean there are a lot of ethical aspects with it, as I think many of you know. AI has an ethical issues. For the time being, we'll try to keep it separate. We'll focus on the technical things here, but these kind of things are getting more and more common. This is also very simple, like a Google Translate. You landed in a city and you were trying to understand the sign. Of course, the biggest challenge is self-driving cars. And this is where like the Teslas and all these things are improving over the years. And miniature versions of these are coming. This is actually some images from the OSU campus over the last several years. These mini vehicles or robots or whatever you can name them are actually distributing food, coffee. You can just order through your iPhone and these get loaded at the cafeteria and then they actually bring it to your offices or the dorms. And these actually is significantly growing, and every month you will see many different places, world, different countries. This distribution of groceries, food, packages, mails are happening like this. Okay, not only this, even in through drones also. Okay. In fact, today there is a news. If you would have seen people in the Great Wall of China nowadays, while touring the Great Wall of China, you can actually order food, and the drone is actually going and delivering the food while you are touring that area. So people are coming up with better and better solutions. So same thing like a medicine, just to give an example, like the doctor, let's say we typically go to a doctor, doctor prescribes saying, okay, do a pathology test for your blood. But if you think of like a pathologist takes typically like 10-15 minutes and pathologists are very expensive. And every day in a hospital, if you see like all these pathologists, there's so much data. So the question is, can we actually build AI training there? And then based on that, we can actually come up with narrow down the solution. We are not saying that the machine will give you the final solution, but at least it will cut down, let's say, from pathologies from 15 minutes to like a 2 minutes, um, and that will actually help reduce the healthcare cost. So just to give this kind of a motivation for the tutorial. If there are any quick questions, we can please post it on the Slack or on the chat. We'll be happy to answer this. But with that kind of a background, now let's go and try to see how these things are getting done in the current system. And this is where we have the deep learning frameworks. And I believe, Amir, you'll take over, or
Yes.
yes. Go ahead, share your slides. And
Okay, so next up, we'll start talking about some of the deep learning frameworks that exist out there. But before we start talking about them, I think let's first talk about the beginnings of DL framework. So, around 2011, 2012 timeframe, these news articles started coming along like, Google is building an artificial brain, and what it basically does is to identify cats in, millions of YouTube videos. This actually got very good coverage in the media, and Google actually used around 16,000 CPU for essentially doing this. So this is ZDNet, this is Wired. It also made it to the New York Times. A very similar study was also done, in another influential paper called Deep Learning with Commodity Off-the-Shelf HPC Systems. And this was published in ICML 2013. And this paper also solves this a similar problem as identifying cats. But this, instead of using 16,000 CPUs, this effort used a couple of nodes, and these were equipped with NVIDIA GPUs. And these used MWPitch, which is a communication library coming out of Ohio State University, led by Dr. Panda here. And MWPitch was used for communications. So, compared to 16,000 CPUs, just a couple of nodes, 4 GPUs, a GPU-based, environment, and then a GPU-aware MPI-based communication library provided similar performance. The reason I'm bringing this up here is that this paper and this project eventually this formed the basis of what is now called cuDNN project and NVIDIA. And cuDNN project is essentially a GPU accelerated library of primitives for DNN. So DNNs, we'll cover in the next section, this comprises of many compute routines like convolution, pooling, normalization. At the end of the day, these all boil down to matrix operations. And cuNN at the end of the day is the library that provides very optimized implementation of these on NVIDIA GPUs. And today, these cuDNN accelerated DL frameworks, these are available in almost all the DL frameworks, that are out there. So, for example, if you have used PyTorch, TensorFlow, whenever we install them, they rely on this, cuDNN to efficiently perform math operations on whatever are the compute devices that you would be utilizing. So this is just some, what are the main objectives of DL frameworks? So these hide complex mathematics. These allow users to focus on DL models. So, for example, we talk about logistic regression or linear regression. This is how the mathematical equation looks like. If we write a primitive Minerva program, which is an old programming language used to solve these kind of problems, this is what the code maps to. If we try and understand how the data is flowing, people study data flows. People also study data flows after doing data partition. But if we want application developers to just focus on their particular application, not go into the details of these. So there are two strategies to essentially deal with these current limitations. So we could utilize parallel hardware, parallel and distributed hardware to do this, or we could be using dedicated hardware architectures for DNN for doing this. And the DL frameworks at the end of the day essentially hides all of these complexities from you and lets you focus on training your own application specific model.
Amir, just 1
So
minute. There is a question. Are we having any issues? One of you says, please use presentation mode. I think it is in the presentation mode. Is anybody else having issue? No? Okay. Please continue. Yeah, I'm seeing in the presentation mode. Yeah,
okay.
okay. Thank you.
So some of the deep learning frameworks out there include Google TensorFlow, for example, Meta's PyTorch. There have been some historicals on ones as well, but today I think it's safe to assume that PyTorch, TensorFlow has evolved into a new framework called JAX. Again, that's also coming out of Google, but these few ones are really popular and frameworks out there that typically you would used to train your models. So looking at PyTorch, so PyTorch is a Python adaptation of Torch. This was written in Lua programming language. This was released in 2016 and has gained a lot of traction. This has several contributors and mainly backed by Meta. The key selling points here are ease of expression and defined by run approach. And this is built upon, makes use of the knowledge gained from previous frameworks like Chainer, Lua, Torch, HIPS. Basically, this was originally a Python library, but some of the core computing code has now been moved down into C, C++. Obviously, this supports, GPU acceleration, and the latest versions of PyTorch do automatic, graph generations and automatic differentiation, which allows, which makes life really easy for the application developers. So these are just some statistics. These are some old stats. So what I just want you to focus here is on this chart at the top first. So, time is on the x-axis, the cumulative GitHub stars on the y-axis, and there's one clear leader, but this time only spans from 2015 until 2019, and the top graph here is essentially TensorFlow. But if the bottom chart here zooms into this crowded space, and in this crowded space, we see one framework coming out in 2017 and really gaining traction and becoming sort of number 2 compared to TensorFlow. And this is PyTorch, as I've mentioned earlier. This came out in 2017. So if we look at some of the latest results, so for example, Hugging Face is a very important model repository that provides some of the really easy to use and widely used models. So if we look at this today, on the left-hand side, we're looking at top 30 models on Hugging Face, and almost all of them have PyTorch implementations. And then there are around 18, 19 that have both PyTorch and TensorFlow implementations. And similarly, if you look at all the models on Hugging Face, almost 85% of the models are PyTorch exclusive. Similarly, if we look at, let's say, research papers coming out of, so a lot of research papers come out, people do experiments or use PyTorch versus TensorFlow. So we have seen that PyTorch adoption grew from just 7% to 80% in 2021. Similarly, there is a website called Papers with Code that keeps track of some of the emerging research, that is equipped with source code as well. So there also we have seen that around in around 2022. Almost 60% of the repositories are PyTorch based and only 11% are TensorFlow. So I mean, with this, we have just covered some of the really high level basics of deep learning frameworks, how they originated. I think it's safe to assume today PyTorch is a very popular framework, and there are others out there as well. Later in our tutorial, we'll cover some of the other frameworks that support parallel and distributed computing on HPC or cloud systems, essentially. So with this, over to Norris for a DNN training section. And there, okay. Yes, over to you, Norris.
Okay, thank you, Amr. You can see my screen.
Yeah.
Okay,
Yes, yes.
okay, very good. Yeah, so over the next two sections, we're going to talk about DNN training and distributed data parallel training. And we have a hands-on exercise that uses uh, both PyTorch and TensorFlow, so the frameworks that Amir just reviewed. But before going into the hands-on, we need to cover some background first to understand what is really happening when we say we're training a deep neural network. So, okay. So this is a very simple example of a deep neural network with 3 layers. Okay. So in here, we don't count the input as a layer. We have 2 hidden layers and the output layer. So 3 layers in total. And a DNN is just a mathematical function. It takes an input and it gives an output. And in here, the weights or the parameters of the network are some coefficients internal to that function. And the process of training a DNN requires us to adjust these coefficients so that if we give it a certain input, it gives us a more accurate output that represents the answer to the problem we're trying to solve. And all of this happens in mainly 2 phases, the forward pass and the backward pass. During the forward pass, we take the input and then we multiply it by the weights. And then this is called propagation. So we're taking the input, we're propagating it to the next layer. And the same thing happen with the layer after until we get the output. Now, based on this output, we will calculate something called the loss or the error. And this will simply compare the prediction that we got, so the output of the network, with the actual expected output, or in other words, the ground truth. So if we're doing supervised training, we already know the answer, but we want the network to give us an answer that is very close to that answer. So based on this, we calculate the loss. How far are we from the actual answer? And then we propagate that error back in the backward pass. And to do that, we calculate the gradients. The gradients tell us the direction and in some sense the magnitude of how should we adjust the weights in order to get a more accurate answer in the future. Another very important concept is the learning rate. So we said that the gradient tells us the direction and maybe the magnitude, but we also need a scalar that tells the network, okay, how much should we update those weights based on the samples or the data that it just saw. So picking a learning rate that is too low will require us many iterations, so many forward passes, many backward passes to reach the minimum value. And in here we can assume that this is basically the range of different parameters or values for these parameters, theta, and j of theta is the error function. And the objective here is to minimize that error. So low learning rate might take us many steps to reach that minimum. Too high of a learning rate might never reach that minimum, might never converge. So that's why it's very important to pick the right learning rate so that with the basically optimal number of steps, we can reach to the minimum. Another important concept is the batch size. And all of this is based on the gradient descent algorithm, which, as we saw, takes many steps, so many forward passes, many backward passes. But there are many flavors to this algorithm. First one is the batched gradient descent, where if we have a data set, the network will basically look at all of these samples in the data set. So it will do a forward pass on all of the samples in the data set, and it will do the backward pass, and only then it will update the parameters. And this pass over the entire data set is called an epoch. And to train a network, we need many epochs. So we need to pass on this data set many times. But this is not very practical because we have like very few updates, right? So we're only updating after seeing the entirety of the data set. Whereas with the second algorithm, stochastic gradient descent, The batch size here is 1, which means we randomly select a sample from the data set. And based on that sample, we do the forward pass, we do the backward pass, and we update the model weights. And then we proceed to the next sample in the data set. So with that, we have many, many updates. In fact, we have n updates. So if we have n samples in the data set, we do n updates. But again, that is maybe too many updates. So it's not practical for like the hardware that we're using. It will take a long time, and we're basing the update only on one sample. So it might be biased to that one sample that it is seeing. So that's why we have something in between the mini batch gradient descent, where we take a number of samples from the data set, randomly select them. You usually select number of sample and powers of 2, 64, 128, 256. So that is a mini batch. Based on that mini batch, again, we do the forward pass, the backward pass, we update the network, and then we proceed to the next mini batch until we finish the entire data set. And this is called still an epoch. And to train the network, we need many epochs. So learning rate and batch size, we need to find these optimal values before starting the training so that we get the best conversion, so best accuracy, and utilize the hardware that we have very well. Another thing to consider here is the overfitting and underfitting. So based on the size of the model that we're training and the size of the data set that we have, we might end up overfitting or underfitting that data on the model. And with overfitting, if the model is too big and the data is very small, so we have very few data samples and a very large model, millions, maybe billions of parameters, the model is not learning, but memorizing the data. So we have many, many passes over that data, and the model is basically memorizing this data. So if it sees data from outside this data set, it's not going to be able to classify it or predict it. So this is how overfitting looks like. We have data samples in orange, and then the blue line here is basically the model, what it's learning, and we can see that it is somewhat memorizing this data instead of trying to generalize, which means, okay, if we see new data, we should still be able to give accurate results. Underfitting is the opposite, is where when data is too large and the model is too small, so the model is not complex enough to capture the complexity of the data, and we end up with a naive representation of the data set. So that's why it is also important to pick the right model to the right data set. Now, some of the applications that are currently very popular when it comes to AI and deep learning specifically, we have two major domains. One is natural language processing, NLP, and it's a subfield of artificial intelligence that focuses on the interaction between humans and computers. We have many different use cases or downstream tasks like machine translation, information retrieval, sentiment analysis, information extraction, and question answering. And for these types of use cases, we use language models. So language models started in the 60s, late 60s with ELIZA. Then we had the RNN architecture in 1988. These are the major milestones. We had the LSTM architecture in 1997, and then transformer architecture came in 2017, which is the foundation of all of these large language models that we know and use today. And it is based on the attention mechanism. So I very much recommend reading this paper. It's called Attention is All You Need, which introduced this transformers architecture. Again, it's the foundation for all of these complex architectures. And then in 2011, we got the BERT and GPT models. And then fast forward, now we have GPT-2, 3, 4, and all the other models like Llama, Gemini, and so on. But another interesting trend that we see here is the size of the model over time. So just between 2019 and 2023, we see exponential growth in the model size. For example, BERT large was 340 million parameters, whereas right now with, for example, Llama 3.1 is 405 billion parameters. So we're talking about what, like 1,000 times the size here. So with this exponential growth, we also need a lot more computational and memory capacity to be able to train all of this, all of these parameters for a single model. Another major area is the computer vision. And the computer vision enables computers and systems to extract information from digital images or videos or any visual input. We have many downstream tasks or tasks that we can perform, like semantic segmentation, where if we have an object within an image, the objective is to segment the pixels, the individual pixels to different objects. Or we can have simple classification. So can you classify the object that is in the image? We have classification plus localization. So find the object, put it in a bounding box, and then predict what it is. And then we have other things like the multiple object detection and the instance segmentation, where we have multiple objects within the image, and we are interested in only in these objects. And the objective is to classify the individual pixels and assign them to two different objects. When it comes to the architectures used for these types of use cases in computer vision, we have mainly two families of models: the CNN architectures, like the ConvNet, LeNet, which came before the 2000s. But around 2012, we got the AlexNet architecture, which really sparked this interest in deep learning and even using GPUs for deep learning. And it performed very well compared to all of the previous methods, mostly machine learning methods, on the ImageNet challenge. And since then, we had more advanced, more deep CNNs like the ResNet, the EfficientNet, the Inception architecture, and so on. And then we have also the Vision Transformer family of architectures, and that came after the introduction of the attention mechanism in deep learning in 2017. Researchers have found that, okay, this is a very good architecture. Can we generalize it? Can we use it for computer vision problems as well? And since then, we had this a very strong architecture, the Vision Transformer architecture, that in fact outperforms some of these advanced CNN architectures. And now the state of the art uses a combination of both of these architectures to produce the best accuracy. So with that, so we covered now the basics of the DNN training. We reviewed some of the popular architectures that are used today, but why do we really need parallel training or distributed training for these architectures? And we saw the trend, right? We saw the trend with the vision models, with the language models. We saw that the size is exponentially increasing. So with language models, we started with RNNs to transformers to BERT to GPT, different versions. Vision models started with AlexNet, and then now we have the vision transformers and the combination between the two. DNNs require a lot of memory and a lot of computation, and we know that larger models cannot fit in the memory of a single GPU. Also, we might have data sets that are very, very large, so millions or hundreds of millions of samples, where training will take a very, very long time to finish. So can we do better than this? So since single GPU training cannot keep up with the data set size and the model sizes, so initially the community has moved to multi-GPU training, where if you have a single node, you can use multiple GPUs within that node, maybe 1, 2, or up to 16. So on a single computer, you can install 16 GPUs and do the training on. But that is limited by how many GPUs you can install on that one computer, right? So that's why we need multi-node or distributed training, where we have multiple nodes on the cluster, each one has multiple GPUs, and then somehow we need to communicate or synchronize between these nodes so that they all work on training a single deep learning model. To do that, we have different strategies. The most popular one is the data parallelism strategy, where we have multiple machines. Each machine will have a replica of the model. So it will have a full copy of that model placed on it. And then each machine will see different data. And then it will learn from that data. And we need to synchronize between these machines so that they exchange the data that was learned. Another method is the model parallelism, where the model does not fit in the memory of a single GPU. That's when we need to split it across multiple GPUs or machines. So it could be a CPU or a GPU. And then we basically propagate, as we propagate through the network itself, we also need to propagate through the participating machines, right? So we need to communicate whatever the output is or whatever the gradients are in the backward pass. But this is usually it's very slow, because if machine one is basically done processing its part, it will sit idle until all of the other machines are done, right? So we're wasting a lot of resources. That's why we need more advanced hybrid, maybe model plus data parallelism, to be able to take advantage of the resources that we have, and at the same time allow training these very large models. So for this section, we're going to focus on data parallelism, but later in this tutorial, we're also going to visit more advanced methods. So data parallelism, why do we need it if you have 1 million images or more than that, 100 million images? It will take forever to train a model on a single machine. The solution is, let's use multiple machines and see what happens. So now we have 5 machines. Each one has a replica of the model. Each machine is seeing different data samples, and we get different outputs, right? The problem here is that if we basically rely on the output of each single machine independently, we're going to train 5 separate models instead of one model, right? And each model will be an expert on the data it was trained on and not on the entirety of the data set. So that's why we need some sort of communication between these different machines. So to do that, we use the MPI or reduce operation. We're going to talk about or reduce more in the upcoming sections. But on a high level, the job of or reduce is to take the gradients, right? We said that the gradients are the values that tell us in which direction should we update the weights and how much should we update the weights. So we have local gradients, different gradients on each machine, and we use MPI or reduce to reduce these gradients or sum them up, right? So it's a summation problem. So if you see here, we start with different gradients, right? But we end up with the same gradients. And these values within this 3x3 table or matrix are the sum of the local gradients. So 1 plus 1 plus 2 plus 5 plus 3 is 12. And we see that value and this place is the same on all of the machines. So now we have the global gradients. So let's take a closer look at this workflow from beginning to end. The first step, we have the data propagation. We said we're going to split the data. So we're going to take a batch from the data set and we're going to split it into mini batches. Each GPU is going to get different data samples. And in this case, we have 4 GPUs, and each GPU will have a replica of the parameters of the model. And then based on the data we got and the parameters that we have, we're going to do the forward pass. We're going to get the output, calculate the loss, and then we're going to do the backward pass to get the gradients. Now we have the local gradients on each machine or each GPU. These are different gradients. That's why we do MPI or reduce to sum the different values, and we end up with the global gradients on all of the GPUs, and only then we do the weight update. So based on these global gradients, we're going to update the model parameters, and then we're going to proceed to the next iteration in the training process. Now, if we have multiple machines, we will need to, in many cases, increase the batch size. So let's say we have one GPU, we start with one GPU and the batch size is 32. As we move to two GPUs, we're going to have 32 on each one, so it's now 64. And if you can imagine if we use 1,000 GPUs, this is called weak scaling, where we keep increasing the batch size as we add more resources. The problem with that is, as we increase the batch size beyond a certain point, and this is architecture specific, so for different model architectures, we're going to see this point happening at different locations. But for this ResNet architecture on the ImageNet dataset, after 8K, using the Atom optimizer, we're going to start seeing degradation and the validation error. So basically, we're losing accuracy as we increase the batch size after a certain point. This is bad, right, that we're losing accuracy, but it's good in terms of performance. Because if we do weak scaling, that is increase the batch size as we increase the resources, it's very good for scalability and speed. So this is something to keep in mind. We need to keep a balance between these two things. And there are more advanced techniques where even with very large batch sizes like 32, 64K, or even 128K, we still maintain the same accuracy. But we need to be aware of this issue, this problem, when we do the training on very large scales. We also talked about the model size. We said that the model size is increasing exponentially, right? So what do we mean by model size exactly? So there are two metrics to measure the model size. One is the number of parameters. So how many weights do we have in the model? And when we say BERT is 340 millions, that is basically the number of weights or number of parameters. But also another metric is the model depth. So how many layers do we have in the model? And maybe one other way to put it is the number of parameters is the width of the model, so how wide it is, and then the number of layers is the depth of the model. So these are two things to keep in mind, because even if you have like low number of parameters, if the model is very deep, there are less things to do in parallel at the same time. So maybe it is not the best idea to split this model on multiple GPUs. One last thing. So we talked about overfitting and underfitting for large models and small models versus large data sets, small data set. But like, when is it better to use a single machine versus multiple machines within the same node or across multiple nodes? So the idea here is that as your network size, or basically the model size, if it is very, very small, and if your data is also small, then your best bet is if you do it on a single machine. That is your best option. You're going to get the best performance out of it. But if your network size increases, maybe you'll need multi-GPU training. Same thing when your data increases, you'll also need multi-GPU training, even for the small model sizes. But if you have large models and large data sets, then you'll definitely need distributed training. Otherwise, either your model will not fit in the first place in the single machine, or if your data set is very, very large, it's going to take a very long time to finish the training. one last thing to consider is the basically the architectures that are being used, the GPU architectures, right? Or the processing architectures. So if you have homogeneous architectures, that is, all of the GPUs are of the same type. So they're all A100 GPUs or V100 GPUs. Then we expect all of them to start the training step at the same time and finish at the same at the same basically time. But what if this is not the case? Then we might need asynchronous training, where the GPUs will not need to wait until the end of the training step to update the weights, but it can do it right away. And later on, we'll synchronize these different GPUs. But this has a trade-off, right? So with the asynchronous, we're gonna get more epochs per second because now we can overlap things, right? We don't have this barrier or wall where we need to wait for all GPUs to finish until we do the update. So we're gonna get more epochs per second, but accuracy per second will drop, meaning since the different models are updating based only on their local gradients, we're gonna see degradation in the accuracy. So these are two different techniques, but if we have homogeneous GPU architectures, it's always better to use the synchronous training technique. It will lead to higher accuracy, and when compared to performance in terms of epochs per second, we're not going to see basically a lot of degradation in the performance compared to the asynchronous training. Next, we're gonna look at hands-on exercise. This is DNN training using PyTorch, and I think we're short on time. So what we can do, I can run these things on my end, but you're also welcome to try these exercises. They are available on GitHub under this link. And then the goal of the exercise is to train a DNN on PyTorch and TensorFlow using Horovod. So Horovod is a distributed training framework. It is a middleware between the communication layer, the message passing interface layer, and the deep learning application. So it sits between PyTorch and the MPI or Nickel library. And we're going to use that for this example. We're going to train the ResNet 50 model on a synthetic data set. So there was a question earlier in the chat, do we need to download a data set? No, this is a synthetic data set, meaning we're just generating random values because we don't care about the accuracy in this case. We just want to see how are things scaling. If we run it on a single GPU versus multiple GPUs, what is the expected throughput? How many data samples are we processing every second?
Navras, might be,
Yes.
let's give a little bit of pause just to see if people have any questions before we go into this
Sure.
demo. Any questions from anybody? Please post it on the chat or raise your hand. The basic concepts which you introduced in the previous section. Okay, looks like there are no questions. So then, Navras, please proceed. Yeah. Or just one question came. One question came on the chat. You can read the chat. A large batch size is bad for accuracy. I think could not understand why it is so. Did you observe the same trend in different data sets? Yeah.
Yeah, that's a great question. So let me go back to this slide. So why is large batch size bad for accuracy? Let's assume we have a very large data set, maybe I don't know, 1 million samples, either text or images. So yes, we see it across different data sets. We have a very large data set, and then we take a batch size, let's say half of that data set. Okay, so 500,000 samples. And based on these samples, we're going to perform the forward pass, the backward pass, right? Backward pass will calculate the gradients. Gradients will tell us where to move our weights, in which direction should we move our weights, and what is the magnitude. But since this model update is based on a lot of different samples, right? It loses its meaning, right? Because we are averaging across all of these samples, and we're doing somewhat of a small update to the model weights. So in comparison, if we have let's say a batch size of 64 or 128, we are basing this update on more local, basically local data or local gradients that are specific to these samples that we are seeing. Now, there are some papers that go into the math. I'm just trying to provide some intuition behind the reason that large batch size is bad. But there are some papers that do explain the math. They are very, very interesting and detailed papers. So this is one of them. If you go to this paper here, you'll see the basically mathematical reasoning for why large batches are bad for accuracy. Another question, when updating parameters, does it do an average division by 4 on the global gradients? Yes. Again, that's a great question. Yes, there will be averaging. So this is based on the optimizer that is used. So if we use SGD, stochastic gradient descent, as an optimizer, or Atom, then yes, we will be averaging the gradients. So meaning we're doing the summation operation with the all reduce. We're gonna distribute these global gradients back to the different machines. Then we're gonna average all of them, meaning 4 GPUs, we're gonna divide by 4. So yes, you are right. Thank you, Iben. Okay. Any other questions before we move to the lab?
Okay, let's continue. There are no
All right.
questions in the chat. Yeah.
Okay, so again, if you're interested in running these labs on your machine, just you can visit this link. I'm gonna run them on my end and show you the results. So this is on the RA2 system. This is a system at the Ohio State University. We have V100 GPUs that we will be using. So NVIDIA V100. We're gonna see the single node performance and compare it to the multiple node performance. And in here we have a single GPU on each node. Okay, so the first thing we're gonna do is srun. Okay, maybe let me just copy the command. So we're gonna run this run PyTorch benchmark single, so a single GPU, and it's a bash script. It will call this script here Python. So we're gonna launch Python. We're gonna launch this PyTorch synthetic benchmark. So again, synthetic data. We're not using an actual data set. Batch size is 64. The model we're testing is a ResNet 50. And we're gonna run for 5 iterations and take the average, just to be sure that the data is not skewed. We're capturing the actual throughput here. So again, this is on 1 GPUs, and we see that the performance is around 337 images per second on the single GPU. So if we have a data set that has 1,000 images, you can say that this will take 3 seconds, almost 3 seconds, to pass the entire data set. Now, if we do this on 2 GPUs, so instead of running the single benchmark, I'm going to run the multiple node benchmark. I'm going to tell the launcher to use 2 nodes. So in here, we're using MPI. We're using the env-pitch library to launch these. We have the same script launching on the 2 different nodes, and the communication that is happening in the background will happen through the env-pitch library. So the all reduce operation will happen through the MPI library. So in here we see it's exactly the same benchmark. We're running on 2 GPUs. And then we see that there is a very small overhead. So this is the throughput on a single GPU. It went from 337 to 326. And then the combined throughput is around 652. So we doubled, but not exactly double. It's like 1.9x, and that is due to the small communication overhead. So that is why it is very important to optimize your communication. Um, if you use a bad communication operation, you're gonna see bad performance. But if you use um, like a well fine-tuned MPI library or communication library, you're gonna see good scaling, good scalability. Now let's go to the second lab, and please post your questions in the chat if you have any
Yeah.
questions. The second one will be the same benchmark, right? So we're gonna do the ResNet 50 on the synthetic data set, but we're gonna use TensorFlow instead of PyTorch this time. So let me go to the terminal and post the command here. So exactly the same benchmark, the synthetic benchmark, same batch size, ResNet 50, and we're gonna run it for 5 iterations. Oh, did I stop sharing? Sorry about that. Okay, so it's around 340 images per second on the on the one GPU. Now we're gonna run it on the 2 GPUs. So as you can see, we have 2 GPUs that are running with all of this is output from TensorFlow itself. It's saying that okay, it's using cuDNN or 1DNN. It's recognizing these GPU devices on each node. Tesla V100 with 32 gigabytes of memory. And then this is the throughput we're getting on the single GPU. And this is the combined throughput. So combined throughput is around 630 compared to 650 for PyTorch. But what's interesting here is that TensorFlow does better on the single GPU. So 340 on the single GPU compared to 337, slightly better. And that is all implementation dependent. So different frameworks will give you different performance for different models on different data sets. But more or less, the performance will be the same for these simple use cases. So with that,
And Navras, it will also depend on the GPUs you use. Am I right? The GPU, whether it is a V100, uh, Volta, Ampere,
yeah,
Grace Hopper. So
absolutely. So this is the V100 architecture. As we go to the A100, we're gonna expect something like 750 images per second instead of 340 on the single GPU. And with the H100, it's like 1300. So with each GPU generation, the performance is doubling or even more than that. So it all depends on the GPU architecture, the underlying interconnect, and also the configuration that is being used. And that is what will be explained in the next section. But I believe there is a question in the chat.
yeah.
How is error calculated in back propagation of unsupervised learning? That is also a very great question. Let me go back to that slide if I can find it quickly. Okay. So with supervised learning, we said that the error is calculated by comparing the predicted value to the ground truth value, the value that we know to be correct. The human labeled that value and said, Okay, if you get something similar to it, then good. You don't have to change your weights, but if it's different, then change your weights. Now, what happens in unsupervised learning, we have so many different techniques to do unsupervised learning. The perhaps the most popular one is called self-supervision, where let's say you have a text, a sentence, right? A sentence with 5 words in it. You cover one of these words. So cover the middle word and then tell the model to predict the middle word. So a human is not providing that text, right? You can just scrape it off the internet and then cover a word in it and ask the model to predict that word, right? And if it's close to the actual word, you're not going to do anything to the weights, but if it's not close to that word, then you're gonna adjust your weights accordingly. So this is one form of unsupervised learning, but there are also other techniques. I hope that explains.
Yeah, so Norris, you that key takeaway slide, I think I
Oh,
interrupted you. I think
did
we
I
need to
skip
cover
that?
that.
Okay.
Yeah, yeah.
So yeah, key takeaway. So deep learning models can be trained in different ways. We saw different deep learning frameworks like the PyTorch and the TensorFlow. For this exercise, we used Horovod, but also there are different distributed middleware frameworks like DeepSpeed, Torch distributed, TensorFlow distributed. We're gonna look at DeepSpeed in Lab 2 in the later section of this tutorial. So running single versus multiple GPU jobs is similar. So meaning if you take the same PyTorch script, you just need to add a few lines to change that script to make it basically multi-GPU compatible. And then Horovat, these distributed DL middleware frameworks can be configured with different communication backends like MPI, Glue, Nickel. We're going to explain those in more details in this very next section. MVAPitch Plus, the MPI library from our lab at OSU, is CUDA aware, meaning if you have GPUs on your system, it will be aware of the presence of these GPUs and it's going to optimize the communication accordingly. And then if you're interested in installing these frameworks, this full stack that I've just used, you can visit this link, idl.cse.ohio State, and we have multiple products actually, multiple packages. We have different user guides, but for this specific package that we just used, it's under Harvard. We have other things for inference, for large image training, all sort of packages that you can use. And then with that, if there are no other questions, I can hand it to Hari.
Sure. I hope you can see my screen.
Yes, yes.
So far, what we looked at was an intro to deep learning frameworks, neural network training, and we also understood why we actually need distributed data parallel training. So far, we were on the demand side, and we were looking at how DL frameworks have evolved to satisfy that demand. Now we are going to look at the supply side to see how the architectures have been evolving to meet this demand. So if you look at it, there are 4 main drivers or pillars, if you want to call it. So you have multi and many core processors, high performance interconnects, high performance accelerators, and storage devices. So all 4 of these combined create the modern HPC architecture, which are driving the current growth in machine learning and deep learning and allowing scientists to create modern architectures, let's say neural network architectures, to solve grand challenge problems. So again, there is a whole gamut of solutions out there as far as hardware and software is concerned. Unfortunately, in the limited time we have picked and chosen a very few of the available architectures. So under hardware, we look at some popular interconnects and processors, both CPU and accelerators. In communication middleware, we look at a few popular communication paradigms to accelerate deep learning operations. So if you look at high-performance interconnects, the first few that come to mind are InfiniBand, OmniPath, high-speed Ethernet, Slingshot, so on and so forth. There are a few characteristics that define a high-speed interconnect. So high bandwidth, low latency are no-brainers. A third one is actually low CPU overhead. Why is low CPU overhead so important? If you look at most applications, they are heavily focused on compute. They only go to multiple nodes when the capacity of one node does not suffice. So communication from the point of view of an application developer is an overhead. Now, on top of that, if you say that an application has to sacrifice some portion of their compute time to communication in terms of CPU cycles, it'll be even worse. So from that perspective, a network which occupies as less of the CPU cycles as possible is best for application developers. There are several software stacks allowing application developers to access these high-performance interconnects. And several of these systems are powering the top 500 supercomputers in the world. Now, if you look at one such interconnect, InfiniBand, it has been evolving over the last 2 decades from about 10 Gbps, now all the way up to 400 Gbps. These come in various form factors. The typical form factor is 4x, where you have 4 pair of cables in one physical wire. This is how the network has been evolving. Right now, we are at this particular juncture in time. So again, as I mentioned, this is not the only high-performance interconnect available out there. There are a few of them, but we just give this to give you a flavor of what is out there. Now, if you look at the CPU side, you have various special purpose as well as general purpose processors out there. This is one such example. This is the Google's TPU or Tensor Processing Unit. The heart of this is what you call as the systolic array. So if there are old timers out there, you would know that way back when systolic arrays used to drive a lot of compute in earlier high performance computing machines. Google has brought that in, and they use a sys style instruction set here. And if you go on to the Google Cloud system, you will be able to use TensorFlow built for this architecture and perform your training there. Now, this is not the only hardware out there. You have what is called as intelligence processing units from a company called GraphCore. So all of these systems have a good hardware available there for deep learning training as well as inference. And they also have an associated software stack for users to utilize these hardware. Now, these systems are available on Microsoft Azure as IPU instances, and you can rent them if you want to. This is another hardware. It's called the Gaudi from Habana. So you have a new version of Gaudi right now, V2. Newer version should be coming up sooner. The specialty of Gaudi is that it has Rocky V2 or RDMA over Converged Enhanced Ethernet chips embedded right on the main motherboard itself, so that you don't have to go away from the motherboard for communication operations. The Voyager system at the San Diego Supercomputing Center has such chips. And because of the high number of interconnect ports available on each chip, you have a very high communication bandwidth and leads to a balanced network. So they have some numbers showing how their solution compares to a Volta 100. Again, these are fairly dated numbers, so take them with a grain of salt. Now, the best possible competition out there for the NVIDIA's GPUs, I believe, is the Cerebras wafer scale engine. So the latest version of the wafer scale engine is wafer scale engine 3. It has close to 900,000 cores, and it is built on a 5 nanometer TSMC technology. It is very high performance. The initial version of Cerebras were limited to one compute device. If you look at the newer version starting from wafer scale engine 2 and wafer scale engine 3, Cerebras has been able to build it out to a cluster scale, particularly targeting large language model training, inference, as well as general deep learning compute performance. It has a lot of communication bandwidth as well as storage bandwidth, as is described here. So these details are for the Cerebras wafer scale engine 2. What I mentioned is for the wafer scale engine 3, those are based on 5 nanometer architecture, not 7 nanometer. So with this, we kind of come to the end of the hardware side of things. I know this does not do justice to all the available hardwares out there, but we just want to give you a flavor for what is out there. No hardware is useful to application developers without a corresponding software to best utilize it. So this is where communication middleware like MPI comes into picture. So if you look at parallel programming models, all of us grew up programming with a common physical shared memory where different processes have access to the same physical shared memory. But these have limitations. And to address these limitations, the distributed memory model came in where processes are aware that they don't have access to the same physical memory, and explicit send or receive operations or communication operations needs to be performed to send and receive data. This is very, very scalable. Unfortunately, it has some overhead because now your code has to be rewritten to be communication aware. A good balance between the two is what is called as a partitioned global address space, or PGAS models, where you have a physically distributed shared memory system, but it exposes a common logical view of the distributed shared memory so that it looks like this to end users. So these are at a high level some common programming models out there for distributed computing. Mostly, if you look at it, the message passing interface is the de facto standard. And for most deep learning, for most distributed data parallel deep learning, all reduce is the communication operation to keep in mind. Now, having said that, deep learning has evolved from its early days significantly. So depending on what sort of parallelism scheme you're using, you could be using pipeline parallelism, layer parallelism, tensor parallelism, a bunch of these different things, or all of them put together. So having said that, now all-to-all, reduce, scatter, all gather, even point-to-point communications are becoming crucial. Now, as I mentioned, MPI is one very popular parallel programming interface. And in our laboratory, we developed the MPAPICH project, which has been running for over 20 years now. And it powers a lot of supercomputing systems out there. And back in 2011, we were the first group to pioneer the concept of what is called as CUDA-aware communication runtime. So nowadays, the concept of CUDA awareness is very common with a lot of vendor-provided stack. But back in 2011, no communication runtime knew how to handle GPU buffers directly. So the modus operandi at that point in time was stage the data to the CPU and then give the CPU buffer, the staged CPU buffer, to the communication runtime. So we rethought this idea and thought, could we give the device buffer directly to the MPI and have the MPI orchestrate the communication from GPU on one device to GPU on another device through any different path? And we choose the best possible communication path, leading to the best performance and best productivity for end users. As a result of this, we were able to reduce the communication latencies by a factor of 10 and almost increase the bandwidth by a similar factor. Since then, a lot of vendors, NVIDIA, AMD, Habana, Cerebras, all of these guys have introduced their own versions of device-aware or CUDA-aware communication runtime. The first and most popular one till date is what is called the NVIDIA's Collective Communication Library, pronounced as NICL. It gives you excellent performance for intranode and internode communication on NVIDIA GPU-enabled systems. Now, although it's called the Collective Communication Library, over its lifetime, it has evolved to support point-to-point operations as well. And now the latest version of NICL supports a variety of collectives like all-to-all, all-gather, all-reduce, broadcast, and point-to-point communication primitives. So with that, we come to the end of this section, describing the latest trends in high-performance computing architectures. And I'll hand it over to Dr. Panda to describe the challenges in exploiting these architectures for deep learning. So while Dr. Panda shares the screen, are there any questions? Okay. If there are not, I think I'll hand over to Dr. Pandit. Thank you.
Yeah, yeah. You can see my screen, am I right?
Yes.
So by now you got exposed to the very broad ideas of the deep learning, machine learning, a quick overview of the architecture. In fact, today morning, if some of you are attending, you got exposed to more details on the HPC architecture. But with the trend currently or the challenge, whenever we are designing these large scale systems, you hear a lot of news about saying Facebook is trying to have this. Trying to do the model training with 30,000 GPUs. Microsoft is ordering 60,000 GPUs. So all these lead to this bullet saying how we want to actually exploit the HPC technologies for DL. So in a broadly, this is kind of a definition or the challenge we are trying to encounter as a community. So how do we efficiently scale out? Many of you must have known about the scale up and scale out. The scale up is basically within a node, if I keep on adding more GPUs or more CPUs, more resources, so that is like whether we can scale it up. But then always there is a limitation. I can only put 4 GPUs or 8 GPUs depending on the server and the chassis. So if I want to use like a 30,000 GPUs, I have to go outside of the node, and that's what is called the scale out. So here the challenge is to how do we efficiently scale out, whether it is a machine learning algorithm or deep learning algorithm or data science frameworks, to take advantage of these heterogeneous HPC resources. So when I call heterogeneous, that means we have CPUs, we have GPUs, and in some of the systems, in fact, we are also getting the DPUs, like the data processing unit from NVIDIA, the Bluefield kind of adapters, IPUs. We talked a little bit about these in the morning tutorial. So like this, a lot of new generation architectures are coming. So when you consider this heterogeneous system, how do we scale out? So so broadly, the ideas are I'll try to analyze into 4 steps. And these are very similar. Like if some of you are familiar with HPC, how the HPC has evolved over the years, the ideas are very similar, but in a little bit different manner. So that's what we will try to see. So let's say you are trying to do an HPC, let's say think of like a weather forecasting, okay, or a drug discovery. And with traditional HPC application, let's say they were not using any AI. So always you try to run on top of some middleware. Okay, so for example, weather forecasting model is running on top of an API library. API library is running on the top of the hardware. So then you have to make sure that your API library itself is optimized. Because if the API library has a lot of memory requirement, it has a lot of computational requirement and communication overhead, then we are not give our end application, which is running on top of the API library, is being slowed down. So same thing we can consider here. So we took a look at some of the like the Navaras introduced the PyTorch, there is a DeepSpeed, many such frameworks are coming. So and these frameworks like based on the examples we saw, like the model propagation, forward, backward, gradient aggregation, they require a lot of this such communication. We saw point to point as well as collectives. So the first goal is to really optimize those operations at the framework level. Then the second one is like a distributed training. So that might be within one node, but once you go outside the node, so this is where the communication overhead is, and you need to really have some good communication runtime. We saw some example like Naurus when it ran lab 2, going from 1 GPU to 2 GPUs, you saw some overhead. We'll try to do some more labs and you will see as you go along. It depends on how the underlying library is being designed, whether it is using InfiniBand, CPU, GPU. If we can minimize that, then we'll be able to scale. Then the third challenge comes is like what is out there inside that runtime. Okay, that is the communication runtime challenges. And here, actually, what is happening if you think of like a MPI library has been there for many, many years for HPC. Of course, MPI has the point-to-point collectives and all, but the new kind of DL frameworks and DL workloads are giving open challenges. And the broad difference here is like we talked about a little bit about the CUDA awareness, because many of these they want to use the GPUs. Then how do we take data from GPU buffers efficiently over the network and bring it back? So this is trying to utilize the CUDA awareness. The second one is called large message collectives. So if you are familiar with a lot of HPC applications, they are iterative in nature. So I distribute the things, they compute, might be some reduce, we are doing all reduce, but typically those all reduce are 8 bytes, 16 bytes. So historically, all the MPI libraries were optimizing all reduce algorithm on let's say only for 8 bytes. But now with this gradient aggregation, that could be very large, sometimes even 4 megabytes, 4 gigabytes. So now you need to rethink, how do we do all reduce or all to all or all gather, reduce, scatter, all those collectives for those large messages collectives. uh, you need to come up with better algorithms. And this has been the research over the last several years. And that's what not only in the MPI library, but that's what NVIDIA's collective communication library, NICL is doing, AMD is doing it, that RICL. Every vendor is trying to optimize that part of the things. Another thing actually we have not indicated here, but what is happening in our group, we have done a lot of research, is on the fly compression. So that means think of like these messages are very large, but then during the communication time, if the cores are idle, we can actually utilize the GPU cores to do compression and then send the data. And then the other side, we do the decompression. But even though decompression has some overhead, we have shown some very good results that you are able to actually boost the performance of the deep learning things. And we have some papers. In fact, our latest MHAPIS Plus has actually already of those kind of algorithms there. So that is the kind of third challenge. And then fourth challenge, as you can expect, it's like a co-design. The concept of co-designing has been there in the HPC field for many years, and that's what is also coming back here. You need to see like starting from the very top level, your different kinds of models, then you are using frameworks, and then below you have an MPI library, below you have the hardware. So is everything actually working together? And if not, can we make design enhancements, let's say to the MPI library, to the framework, even to the hardware features, whatever is available, and then put them all together with a co-designed approach to give better and better boosts. And that's what actually, where when you hear about like, okay, Microsoft is deploying this kind of large systems, Facebook, their internal team are actually doing this kind of operation. All these four challenges are becoming common across all the people, whether you are a commodity cluster user or you are like within these big companies, there are dedicated team who are trying to do. And of course, there are a lot of other challenges which come. We are not outlining here, but that is also becoming very important, like fault tolerance, reliability, all those issues, whatever has been there in the HPC, similar things are also being coming into the AI field. Because if you are running a training for 3 months, GPUs are bound to fail. There will be errors. So how do we recover from those? So there are a lot of work is taking place with respect to either bringing those solutions into the framework level or let's say to the MPI level. How do I do efficient checkpoint restart? So all those are becoming challenges. So what we'll do is, of course, it's a very big field. We'll not be able to cover everything. So the next section will actually try to show some advanced training, distributed training, how people are trying to use some of these designs. And by the way, the morning tutorial and also this tutorial both have been invited for supercomputing conference. And there we have like a 1 day each for each tutorial. And we also have a third tutorial on the big data. So if some of you are planning to come to SC, please join our tutorial. We'll go into very long details because we'll have complete day for each one of these tutorials. We'll go with a lot of hands-on. You will be able to actually run these things on a cluster and get a feel. But for today, we have limited time, so we'll just try to give you kind of a high-level perspective so that you understand the field. So with this, let me hand it over to Nauras. So he will go over the advanced distributed training, and then we'll come back to the inference solutions, and then open issues challenges, and we'll finish. So we have 1 more hours to finish this. Now, Russ, let me stop sharing. And by the way, if you have any questions, please feel free to ask. I know it has been a long day. Some of you might be attending multiple tutorials, but please feel free to ask questions. So we'll be happy to answer. Yeah, we can see now, Russ, there are no questions yet, I see.
Yeah,
So
there
you can
are
continue.
no further questions. Okay, so yeah, this next section will be about advanced distributed training. So what we talked about previously is the data parallel training, where we said the model does fit in the memory of a single GPU. But for now, we're gonna look at more advanced cases within data parallelism and then some of the cases with model and hybrid parallelism, where again, we need more memory beyond a single GPU. So by the way, all of these solutions that we're going to review under data parallelism are again available in the HiDL website that we mentioned earlier, and we also have a GitHub page where all of these packages are available with the code itself. But this is the high level overview of the deep learning stack. We have the MLDL application at the very top, and under we have the different deep learning frameworks like PyTorch, TensorFlow. And then under we have the distributed training middleware. So Horovat is what we used for the previous lab. Torch Distributed is another very popular package. So it is an extension of PyTorch itself. It's not like a third-party library. And there is also DeepSpeed from Microsoft, which this lab will be utilizing DeepSpeed. And then under all of this, we have the communication runtime. With the MVPitch library, we use MVPitch 2 or MVPitch X for the CPU-based training and MVPitch 2 GDR for the GPU-based training. However, with the new release of MVPitch Plus, we're combining both of these libraries, so you'll be able to get the best performance, whether you're using CPU or GPU with the same library, so you don't have to install two different libraries. This is one example of scaling on a very large system. This is on the Summit system with around 15K, 1,500 GPUs. This is the ResNet 50, so the same example that we ran in Lab 1 on the V100 GPUs on the entirety of the ImageNet dataset, so 1.2 million images. So earlier we saw that we get around like 350 images per second on the single GPU. So you can imagine how long it would take for a single GPU to run like on this entire data set. And keep in mind that we need to run this for 90 epochs. So we need to run on the entire data set for 90 times. So with one GPU, throughput is very, very low. As we scale to 1500, we get around how much? I don't think we have the throughput. Oh, yeah, throughput is around 450. Yeah, around 450,000 images per second. And time is 4.5 minutes. So 4.5 minutes for the training of the entire network, or 90 epochs on the entire data set. We can do similar things with the CPU. So this is on the frontier system. And here we have 2K CPU nodes. And here we're using TensorFlow instead of PyTorch. We're with MVPitch 2. The throughput we're getting is around 260,000 images per second. So with a GPU, we saw 450. In here, it's 260. So still like very good performance if you have access to many CPU nodes. So you don't always need the GPU. If you have many CPU nodes, you can run the distributed training and still get a very reasonable performance. On this scale, we were able to train it in only 7 minutes. So again, the entire model on the entire data set. And this is published back in 2019. And this paper, if you're interested in more details, you can find this online. But there are also so again, this is from 2019. So the hardware was relatively well, it was relatively slower to the hardware that we have right now, and that is why we see very slow execution on the single GPU. Now, with these new hardware architectures like the A100 and the H100, the smaller models, the relatively smaller models like ResNet 18, ResNet 34, and even ResNet 50, the model that we ran, for example, are now considered small because like ResNet 50 is around I think 34 million parameters. And right now with the GPTs, we're talking about 300 billion parameters. right? So this is considered relatively small. And what we noticed is that the GPU utilization for these small models, so even on the single GPU, the GPU utilization is low. So we see like as low as 40% utilization for this image size, and for slightly larger image sizes, we see as low as 50% GPU utilization. And the reason is there is not enough parallelism to be executed on the GPU. So the job is small. We cannot really occupy all of the GPU cores and take advantage of them. So the solution here, and if you're interested in the specific, you can refer to this paper, but the solution is, can we exploit data parallelism even further and place multiple model replicas on the same GPU? So previously we saw we have 4 GPUs, let's place one model replica on each GPU and then do all of the forward, backward pass, or reduce for communication, and then we update the model parameters. Now, instead of placing a single model replica, let's place multiple model replicas. In this example, we're placing 4 replicas. So 4 models on the single GPU. If you have 4 GPUs, that's 16 in total. And then we run the training, and communication happens with like within the GPU itself and across GPUs. And this is facilitated by the use of MPS from NVIDIA. MPS is an multi-process service that you can run it on the GPU, and then you use it with MPI. So with an MPI library like NVPitch to be able to communicate between processes within the GPU itself and across the GPUs. And with that, we can see good performance benefits like 30% on the 16 GPUs and 62% on the 16 GPUs. Again, these are with two different model sizes. So this is with Resonant 18 and ShuffleNet. So depending on the model size, you'll get different performance. So this is all with data parallelism. Now let's look at model and hybrid parallelism. There are many different methods, many different techniques. We're going to cover 2, and these are considered the state of the art. First one is the deep speed zero, also known as FSDP, fully sharded data parallelism. This is the name that Torch Distributed uses, but DeepSpeed uses the zero optimizer. So zero itself has 3 stages, so 3 stages of optimizations. In this video that we're gonna see, let me try and play the video. Pointer option, okay. So this is using the 3rd stage, so the stage that gives us the most memory saving. So again, keep in mind, this is for very huge models where we cannot fit the model and the memory of a single GPU. So let's play through this video. Let's assume we have a transformer stack, a model with 16 layers of transformer blocks. We have a data set. We have 4 GPUs that we want to train this transformer model on. So with data parallelism, what we do is we split the data, right? So this should be familiar to what we've been doing so far. And then during the forward pass, we're going to propagate through the layers, and the backward pass, we calculate the error, and we update the parameters. Now, the model itself occupies a lot of memory, especially if we're using mixed precision. So we'll have the model parameters in FP16, the gradients in FP16, but again, the optimizer itself. So if you're using the Atom optimizer, for example, we need a copy of the parameters in FP32, and then maybe we'll have extra optimizer states that we need to keep track of, like the variance and momentum. And we need an actual copy of the parameters in FP32. The reason for that is if we're accumulating gradients and parameters over time, we're going to lose accuracy if we're doing everything in FP16. So we will need to keep a master copy of the model parameters in FP32 in the single precision. The actual computation can happen in FP16. So that's how mixed precision takes advantage of the hardware. Now, with the zero optimizer, 0 stage 3. So this is the basically highest level of optimization in terms of memory. We're gonna shard all of these parameters that we just described, right? So FP16 parameters, gradients, and then all of the other things in FP32. So we're gonna shard these across the GPUs. So now each GPU is responsible for a part of the model. So first is GPU 0 is responsible for this part. Next part is for GPU 1, then 2, then 3. So how are we going to do the training when we split the parameters like that? So if we're doing the forward pass on the very first segment of the model that GPU 0 is responsible for, it's going to broadcast that segment to all of the GPUs. So it's going to send a copy to all of the other GPUs. So we have GPU 0 sending 3 copies to the other GPUs. Then we're going to do the forward pass. And then since only GPU 0 is responsible for this copy, we're going to delete this copy from all of the other GPUs. Now, GPU 1 is responsible for the next segment. So we're going to send that segment to all of the GPUs. And remember, in the forward pass, we only need the parameters themselves. So we only care about this very thin line, the thin blue line for the forward pass. And we're going to do that for all of the segments or all of the shards. So GPU 2 now will send to all of the GPUs. We'll continue in the forward pass. And then finally, GPU 3 will send to all of the other GPUs. And that will conclude the forward pass. So now remember, like the purpose of the forward pass is to propagate the input through these layers and get a loss, right? Get an output compared to the actual output and get a loss. Now, based on that loss, we're going to start calculating the gradient. So gradient is in a yellow here, and we're going to aggregate the gradient, right? So since GPU 3 is responsible for this segment of the gradient, all of the other GPUs will send their gradients, and we're going to reduce them in GPU 3. Now, same thing for GPU 2. GPU 2 is responsible for the next segment, so we're going to send a copy of the parameters in blue, and then we can start calculating the gradients on each GPU. Remember, each GPU is seeing different data, so gradients will be different, and we still need to reduce them. And reduction here means, okay, all GPUs will send to a single GPU their data. And then fast forward, we're going to do the same thing on GPU 1, GPU 0. And now what we end up with at the end of the backward pass, we end up with a different shard of the gradients, the reduced gradients, on each GPU. So if you see GPU 0 has one shard, the first shard, GPU 1 has the second shard. And what we did with gradients previously is that we used them to update the weights, right? And in here, we're going to use them to update the master copy of the weights. So not the FP16, we're going to update the FP32 weights. So all of this in green will be updated based on the gradients. Now we send a copy from the FP32, basically we cast it to FP16, so we can use that copy in the next training iteration. And this is 0 or FSDP on a very high level. If you are interested in learning more, you can visit this link. They also have multiple papers on this optimizer. I recommend reading them. But also, if you have any questions about this, please post them in the chat. I'd be happy to answer any questions you have. Again, the purpose of this is just to save memory, right? So if you see, we started with data basically fully replicated data parallelism. We have a copy of the entire model on all of the GPUs. So let me go back here. You see, this is data parallelism, like the regular data parallelism. We need to save all of the model. So we have redundancy or repetition in the data. Whereas with the zero optimizer, we're sharding the data, meaning now each GPU will hold a smaller part and we can save memory, we can fit larger models on larger systems. Okay, so if there are no further questions, we can move to the next advanced technique, and that is the 3D parallelism. So 3D parallelism itself can use either data parallelism or fully sharded data parallelism, but it also uses other techniques like pipeline, like tensor parallelism. So that hence the name 3D. We have three different ways to do parallelism that we're combining. Pipeline means if you have a long model and you're placing each part of the model on a different GPU, what you can do once a model is, or once a GPU is done with processing its part of the model, you can feed it the next sample right away. And that will help you keep the pipeline or the segmentation of the model. You'll help keep all of the GPUs occupied, which means you don't like you're trying to minimize the wasting the resources or the idle time in the resources that you have. So this is on a very high level what pipeline parallelism is. And then with tensor parallelism, if you have a layer, so in the previous example, we said we have 16 layers, right? So the transformer model had 16 layers. But if each layer does not fit in the memory of a single GPU, that means you cannot split the model horizontally, right? You need to split it vertically, which means the layer itself has to be split now, not the model, but the layer itself. And this can happen with tensor parallelism. So all of these operations that we're doing in the background, they are just matrix multiplication, matrix addition, maybe transposing or slicing. But matrix multiplication is the major operation, and tensor parallelism helps in that. So if we have a very large matrix multiplied by a very large matrix, we can split this operation on multiple GPUs. But it requires a lot of communication. So we need to be careful about how we place these different parallelism schemes in a network topology. So let's say we have 32 GPUs, and on each node we have 4 GPUs. So for example, in this teal color, GPU 0 to 3, this is one node, and then GPU 4 to 7, this is one node, and so on. So within the node, we usually have much higher bandwidth because of the basically spatial proximity, right? That the GPUs are closer, but also the interconnect is faster. So for example, within the GPU, we usually see interconnect like NVLink, which has very high bandwidth, but across nodes, we see something like Ethernet or InfiniBand, which also has like high bandwidth in many systems, but compared to NVLink, it's you can divide it by 4 at least. So that's why we need to be careful about how we place these different parallelism techniques. So the best way to do it is within the single node. So GPU 0 to 3, we do the tensor parallelism because it's very communication heavy. And then if the model fits in the one node, this is great. We can move to data parallelism right away. If not, then we do pipeline parallelism. So this is the second dimension. The first dimension is model parallelism or tensor parallelism. The second dimension, let me use the laser pointer. The second dimension is pipeline, meaning if the model still does not fit in the single node, then let's move to the second node, right? So this is the second dimension. Now, the model, we see that the model does fit in these two nodes with model and pipeline. Then we can do the data parallelism, and that is, let's replicate the model across the remaining nodes, right? So now we have 2 model replicas, but for each replica, we have model parallelism and we have pipeline parallelism. And hence the name 3D parallelism. We're using all of these techniques together. And like keep in mind, for example, pipeline uses point-to-point communication, tensor parallelism uses all reduce, data parallelism uses all gather and reduce scatter. So there are a lot of things that are happening in the backend and in the communication runtime.
Yeah, so let me also add a little bit of comment. So this is what, if you remember, we discussed the challenges. So this is where I think the HPC and AI together are like trying to open up a lot of these challenges. I said like 1, 2, 3, 4. If you remember, like let's say even in the HPC field, let's say you are trying to optimize like a earthquake simulation on a blue gene, or an earthquake simulation on an InfiniBand with a 3D interconnect, or like optimizing some drug discovery application, bio application on a InfiniBand with Dragonfly. So these were the algorithms people have designed, saying how do we exploit the locality of reference, locality of communication, minimize the communication over it. Exactly same ideas are coming into the DL training. Okay, so gradually, I think those are, you will see in the literature, a lot of new papers are coming. So every time new kinds of HPC systems are being deployed, researchers are coming as well as the practitioners are coming up with better and better solution, because the problems are very similar. Whatever has happened in the HPC field, people are rediscovering these into the AI training, and the broad objective is to really reduce the communication and make it faster. So that is the exactly kind of a examples we are trying to give here, just to for you to just to get a feel. Okay, and soon you will see. I mean, those of you are familiar with SC, the Gordon Bell prizes are given like for a given system, how best they deliver the performance. And gradually, I think some AI solutions are coming there. You may see even in the future, even these kind of solutions will go to the Gordon Bell prizes. Okay, because people are totally exploiting at every level how we can reduce the communication. And every time a new GPU architecture comes, CPU architecture comes, and interconnect architecture comes, storage also makes a big role also. So then you need to rethink how to exploit these different parallelism. Okay. So any questions on this section? I know Norris will go through another two demos. Might be let's get started, and then if there are any questions, please post them on the chat, and then we'll go into the inference and then try to conclude.
Okay, so lab 2 will be about out-of-core DNN training using deep speed. So out-of-core means a model that does not fit in the memory of a single GPU. So the objective of this lab is to test an out-of-core DNN on a single node, single GPU. We're training the BERT model. So this is a transformer-based architecture with 2.5 billion parameters. And then we're going to train the same model, but on 2 nodes and see the difference between the 2 experiments. Okay, let me pull up the terminal here and zoom in. So this is lab 2. We have 2 scripts. Let me... Okay, so we're going to run the first script, 1 node. We're going to run the strain BERT single. We're using the deep speed framework. In the host file, we're specifying the nodes that we are using. Again, this is just 1 node, so we'll find 1 host in the host file. And then we're running this strain BERT script, Python script. We're checkpointing, so we're trying to save the model after a couple of iterations. This is the size of the model, so we have 192 layers. So this is how deep the model is. And then this is the forward network dimension, the hidden dimension. And then we're just trying with batch size of 1, so the smallest batch possible. And we'll see if it does fit in this single GPU, single V100 GPU. The V100 that we're running on has 32 gigabytes of memory. So 32 gigabytes, and we're seeing this out of memory error. So it's saying CUDA out of memory, try to allocate 16 bytes on this GPU, and it failed. So if I do, let me allocate an actual node. And just show the hardware. So now we're on node GPU 5. If I do NVIDIA SMI, you see that we have on each node this V100 node with 32 gigabytes of memory. And what we saw earlier is that even with this 32 gigabytes, we're running out of memory. So maybe we should try it on 2 nodes and see what happens. So again, this is the same model that we're trying to train, but now we're using 2 nodes. And we allocated nodes 1 and 2 with 1 slot on each GPU. That is one GPU on each node. Exactly the same model, same depth, same batch size. And we're running for 10 iterations. So this is all of the output that you see here is the initialization from the DeepSpeed framework. And in here, you can see the model is being downloaded from the Hugging Face hub. DeepSpeed runs on PyTorch, so you'll see a lot of PyTorch output as well. And now we see that the model creation is done. Now we're creating the DeepSpeed engine for communication. So the engine is created, and we see that the Torch backend and DeepSpeed is using MPI. So since we're using the envapitch library, we'll see MPI here. And then we'll see a lot of output now. It's basically running these 10 iterations. So for each iteration, we're going to see step. So step is the number of iteration. We see the learning rate and the momentum that is used. These are hyperparameters. But also we can see the memory that is allocated, and then the max memory allocated. So memory allocated means at this specific moment how much memory is allocated, but during the run itself, like the entire iteration, what was the maximum memory needed? So we can see that it's around 19 gigabytes. So, but that is per GPU. So 19 plus 19 is around 38, right? And that is why we were running out of memory on the single GPU, because the single GPU is 32 gigabytes and we need 38 gigabytes. So now if we split it on the 2 GPUs, we can run it, and you can see that the process exits successfully. So which means we ran these 10 iterations successfully, we trained the model on the data, and the model is now saved. We can use it later for inference, or we can continue the training on. So this in the slides, we see the expected output, exactly what we saw in the run itself. And then on the two GPUs, we see that it completes successfully. So with that, we can move to distributed inference solutions. But before, okay, I think what collectives are used in tensor parallelism? Yeah, so with tensor parallelism, you'll expect to see O reduce as well, because And basically we talked about this attention layer, right? And transformer models use multi-head attention, and there is inherent parallelism in multi-head attention in that we'll use different parts of the model to calculate basically different representation of the input, and then we're going to do a reduction operation or a summation operation. So that's a very good use case of all reduce. So with tensor parallelism, we use all reduce. There is another question. Earlier, InfiniBand, NVLink, etc. were mentioned. Where does RDMA and RoCE fit into the communication structure? Do these use Ethernet, InfiniBand-like protocols, and what kind of things are transferred with RDMA model parameters and input data? So perhaps the first part of the question, yeah, Dr. Panda.
Yeah, so I'll explain. So what you saw, like again, there are all these different parallelism. As Nora said, like sometimes it depends on, let's say you have 4 GPUs or 8 GPUs per node. So this is where NVLink is being used, okay? But that is like a scale up. But once we are going outside, so this is where InfiniBand or RoCE, Slingshot, all these are used. So altogether, if you see like for a large training, we are using both scale up and scale out. So we are using technologies like NVLink. We are also trying to use the RoCE. Now, how exactly they get used? That's what that software stack we indicated. Okay, so this is where variety of solutions are there. If you think like take like a hoverboard, very simple one. Either it can go through like NVIDIA, let's say it is a NVIDIA hardware, it goes through the NVIDIA Collective Communication Library, and that library is actually built on top of InfiniBand. Okay, it uses all the RDMA APIs and all which we discussed earlier. Okay, or alternatively, you can go through API. That's what we are trying to show, because API also has the support for the collectives. Okay, you can also have mix and match. We also have those kind of solutions. So then you can think of like that's what I indicated, like the research challenge 4. There are multiple layers starting from your application. It is going through some kind of like a deep speed, hoverboard, PyTorch distributed. Those are, we call it framework. Then the framework is using a communication runtime, either using Nickel, RECL, or MPI, any of those things. So we are talking about all these model parameters, input data, and all. This is like coming from the very top, right? So in order to optimize, you need to make sure that everything is working together. Okay. I hope that answers your questions. Any other questions before we go to inference?
So just one comment on the previous question. So
Yeah.
what things are transferred, model parameters and input data? So usually we do not transfer input data. We just transfer model parameters. Input data is on a shared file system, which means all the nodes have access to the same data. And it's only that during the execution, different nodes or different GPUs will access different data samples on that file system. So we do not require communication for that. What is communicated in most cases are the model parameters or the model activations. Just to clarify.
Thanks for clarifying that. And again, all these systems, just like HPC systems, they are using Lustre, NFS. I mean, think of any traditional HPC systems also, you have the same issue. I mean, we have used input data and then it has to be loaded to the CPUs, GPUs before the operation can start. So the idea is also very similar. The only difference is that here, how we load the batches, mini batches. So there is a certain way in which we have to take the data and then for the training. Okay, so if there are no other questions, Amir, please proceed.
Sure. Okay, so next up we will now get into distributed inference solutions. So far we have been focusing on retraining, basically deep. I mean, we just also simply call it training. But more recently, we have realized that the community has realized that deep learning inference is also a very important workload. So when we compare this with the training phase, So training is all about model learning, and basically it's more, we are given input data, and we would like to go through process that data as fast as possible. So essentially we are more concerned about the throughput. Inference is a different workload in that context, because this is, we could do inference in batch mode, like process many input images, or whatever is the different types of inputs in batches. However, typically, the kind of interactions that we do with Chat GPT, this is user facing. We just send it a query, and we expect it to respond in a timely fashion. So in this context, latency, or how fast it's, or responsiveness back to the user, is an important metric for the inference workloads. And this is closest, to the user. And if we look into different aspects, typically speaking, there is smaller batch size involved. Um, and another challenge is that the user end request might, they will arrive randomly. There is no, when we are doing training, we can choose our own batch size, depending on how many GPUs we have. But, we don't have that kind of luxury with inference workload. So requests could come in any volume. They could arrive randomly. Um, we don't typically update model weights. So for example, if you look at this top figure here, so this is the top here is training, the bottom here is inference. So when we are doing training, there is a forward propagation, followed by this error calculation and a backward propagation. And the reason we do this backward propagation is we would like to adjust the model weights, and we would like it to do better for the next batch of data. But in inference, the model is static entity. We are not updating the model weights. It has gone through all the rigorous testing. It's giving acceptable performance. So whatever model we have, we simply engage in forward propagation there. Again, response time, how fast do we get back to the user, is essentially going to be the most critical thing. So, I mean, in this case, a couple of aspects to think about inference is, so as I mentioned, there is online versus offline, or batch inference, essentially. Online basically means that, I'm a user here interacting with Chat GPT, or let's say I'm sitting on WhatsApp and talking to Meta AI, and how fast do I get the result or the image generated by Gen AI application? That matters to me. On the other side, we could also engage in batch inference, and this could be employed for processing large volumes of data. So I mean, in this case, again, while throughput is important for online inference, latency is relevant and important for online inference. Throughput is more, appropriate metric in the case of batch inference. And batch inference typically, matches the training workload. Another interesting aspect of inference is that, we don't necessarily do inference on HPC systems or very powerful systems. I mean, we could do that, but typically, we engage in cloud inference, for example. So we have resources, we are looking for better scalability. However, inference also happens on edge systems. So for example, this WhatsApp, for example, it's installed on your whatever device you have in your hands, phone device. It would essentially work with you on whatever compute power is available on your own end devices. And if we think about autonomous vehicles, or let's say IoT, then we are thinking about, or we are working in a very resource constrained environment, where we would like to make sure that we get acceptable performance. So with this, we'd like to talk about this one piece of work that we have engaged in, recently. So this paper was published in an fog and edge computing conference. This is last year. And in this work, what we have done is we have actually used quantization to improve inference performance on edge devices. So we worked with a couple of edge devices. We worked with the Raspberry Pi 4, and the other device was, let's say, you're doing inference on your own desktops using Intel CPUs. So what basically quantization means is that we could utilize, let's say, leaner um, data types, for example, FP16, int16, or int8, instead of using the default FP32 to represent the weights and activations in DNN models. I mean, I will not be able to go into a lot of details, but people have researched that if you're, let's say, using FP32, do we actually require the full range of FP32 for storing weights and activation? And people have found out that we are you know using a very small range, so which is encouraging, because then it gives this possibility to use FP16, or even use quantization aggressively to convert these floating point numbers into integers and utilize, let's say, int8 or int16 data types. So there are dual benefits of doing this. We'll be able to fit a larger model into a resource constrained edge device if you are able to do that. So size reduction is one obvious advantage, and another advantage is that this could also lead to better performance in terms of lower latency and higher throughput. So I'll just these experiments are done using MLPerf. So MLPerf gives a very nice benchmarking strategy. So we utilize that. I'll just explain one of this, the chart on the left here, which is MLPerf has different benchmarks: single stream, multiple stream, and offline. So here we are talking about single stream. And in single stream, we worked with a couple of networks, models, DenseNet and VGG19. And I'll just talk about VGG19. So in this case, we worked with OpenVINO. These yellow bars represents OpenVINO. So OpenVINO is a training and inference framework geared for Intel CPUs. And then these blue lines are essentially PyTorch. So in this case, there are two data points for VGG19 for PyTorch. We plotted this, FP32 performance, and the latency is around 31.6 milliseconds. But when we run this int8 version, not only do we get like 4x reduction in memory, but we also get around 2.1x better latency. So lower is better. So for that reason, int8 static quantization version is doing better. So similarly, we see similar performance trends for VGG19 when working with OpenVINO. And then we also have other results with multi-stream. The format is pretty similar. I mean, the speedups are more pronounced, and also for basically the offline mode. So in multi-stream and in offline, we are working with multiple inputs. We are just not, in single stream, we just process one input and then go to the next one. But in multi-stream, and in offline, we are running inference on multiple inputs at a time. So this gives us, more opportunity to optimize. So another work that we recently published in HiPC conference is called Flower. And this basically gives an efficient parallel inference for LLMs. And this implements a technique called temporal fusion. So if you look at state of the art when we did this work was faster transformer. Today, I think TensorRT LLM or VLLM or Hugging Face inference runtime, those are considered standards. So in faster transformer, it implements these two strategies to handle multiple incoming requests. So one is called dynamic batching, and the second one is called concurrent instances. So in dynamic batching, what we do is, your request could be coming in, request 0, request 1, request 2. you would just wait for a certain time window. So for example, this is a predefined, pre-configured time window. So in this figure, we are waiting for almost 500 milliseconds. And after that, whatever requests we have received, we'll put them all together, in a batch. We call this dynamic batch, and launch kernel, a CUDA kernel on NVIDIA GPUs, for example, if you are working with NVIDIA GPUs, and basically do the inference. But obviously, if we look into this scenario, so request zero is unnecessarily waiting for majority of this 500 millisecond time window until we could start processing request zero. So the solution from our lab, or what we call temporal fusion, is that we have a mainstream inference kernel which is running all the time. So as soon as a request arrive, we have architected a solution that we are able to start processing that request instantly as it arrives. And this is obviously um, gives us performance boost compared to dynamic batching and concurrent instances. So when we implement this, one of the techniques that is also implemented is what is called, we have to memory reordering. We have to, since all these requests get processed in a CUDA kernel, and in CUDA kernel, it's always best to have things in a batch close to in close proximity in terms of space. So I mean, it's perfectly possible because we don't know how long a request is going to run. So it's possible that the requests that are sitting between. So for example, this request 5 and request 7 in this particular case, they get done before the other request. So in this case, we'll then have to essentially relocate our request so that our CUDA kernel can execute efficiently whatever requests are there to process. So let's, so I won't get a chance to show you some of the performance numbers, but Flower, if you go and look at the paper, we are approximately seeing significant speed ups around 15 to 20x speed ups compared to faster transformer. So with this, now I'll hand it over to Dr. Parda for open issues and challenges.
Maybe you can stop sharing, then I'll.
Yep.
Okay. So in between, let's if anybody has any questions, again, we'll be very happy to take. We are almost coming up to the end of the tutorial. Okay. So here we'll try to finish up with some of the open issues and challenges. As you saw, like this field is like a emerging. I mean, so within the next generation hardware, next generation model, there are a lot of excitement. People are coming up with better and better solution. In fact, every day, if you think of like archive or any of the conferences these days, lots of papers focusing on all the different layers. So here we just for food for thought, we just want to give like some of the open issues along 4 directions, like convergence of MLDL, HPC, scalability, large batch size training, and how to have some kind of a standardization in the field. And of course, like how the kind of with an open exchange, making AI, those kind of things, what is happening. So for some years, at least 2, 3 years back, these ideas always started saying, are we like trying to this convergence? How to take place is like a machine learning, deep learning, or data science. Is it an HPC problem or not? By now, I think it has been very well established. Okay, as you saw, like a distributed model, DNN training is definitely an HPC problem. Inference, it was not, but gradually people are discovering. That's why we are saying not everybody is following that, depending on your situation, how you are doing the inferencing. Let's say you have a dedicated device and then you have actually a near edge where your model is, and then you are just gradually going online. That itself might be good enough for you. But Amir indicated like a lot of these examples where the large amount of data is coming, you have to have the or a lot of inference requests are coming to a single server. So those are actually HPC problem. Okay, and And also at the same time, like the support for the machine learning frameworks on HPC system is also improving. And all the very latest systems, if you take a look at the top 500, as you know, like there is a previously they used to only present the HPL, like a high performance lean pack. Now with even those HPL also, like they have all these, like now people are coming up with FP32, FP16 numbers. So these are called the AI performance. Okay. So all the machines, they are now trying to say both the performance kind of thing. And this is where also there is a debate going on, like a exaflop system might be need not deliver exaflop on a strictly kind of an HPC problem. But for AI problem, it can actually do, because you are reducing the data types, like going to 16 bits. Even there is a discussion going on to like FP8 and FP4 even. Okay. So as we saw, like there is a some of the needs are exact match, because all the type of things what we saw, like a the DL training is basically under the hood. It's all matrix vector, tensor, those kind of the applications, and these are very computational intensive, and that's why we need all the CPU, GPU, DPU kind of things to accelerate further. The only thing is that these runtimes need to be modified, and that's what we are seeing in the community. The underlying library, like you have to handle large message communication, you have to have CUDA aware communication, so that all these libraries are being redesigned to cater to the emerging trend. So then we had some discussion. There were also some questions. People are playing with all these large batch size. It helps to improve the scalability, because there are lesser communication and more compute before synchronization. But there is always a large limits to the large batch size. And this is the community is helping or exploring a lot of better solutions. And then if you see the pipeline, I think we touched a little bit, didn't get time to go into details, especially starting from the IO or from the file system. If you think the entire workflow, like you are taking the batches, many batches, operating them, communication, so you need to optimize the entire operation. And this is where also people are working. We just focus mostly here on computation and communication, but in real scenario, you also need to take the IO also into account. Now, is there a limit in the DN size? I mean, it's continuously increasing. A few years back, like just a billion parameter was big. Now we are getting into half billion. There is a trillion parameter consortium. It stands for TPC, which is being led by Argonne. A lot of organization all over the world are participating there. So please take a look at that. And we also talked a little bit about this out of code training. That is also becoming important, even though if you think of like NVIDIA, the each like a Volta, Ampere, and all the memory size is increasing, but the model sizes are also increasing. So there is always this, there is a limit that the model may not fit everything. And we saw some of the examples, that small animation video Norris went through, like the zero speed, how they are trying to do these things. Now, as this field is also evolving, people have been debating, is there some standard benchmarks or standardization? We are not there yet. If you remember, like a message passing interface, those of you are familiar in HPC, prior to like a 90 mid 90s, every system had their own communication library. And they are not compatible. Then the MPI standard came, and that actually helped to isolate the applications. If you have written any your parallel application using API, then it can be portable. Need not be performance portable, but it is at least portable across things. So that kind of things have not come, but gradually what is happening is, as you saw, like a few years back, TensorFlow was the framework. Everybody was jumping in. Then now the PyTorch, distributed PyTorch has come. Now the deep speed has come. So it is gradually evolving, and might be there will be a point where we will see like some framework which will be defined as like a kind of a standard, but we are not there yet. And then the similar things are happening with respect to benchmarks also. How do we measure the performance? Of course, over the last several years, there have been a lot of different benchmarks have been proposed. But what is gaining more momentum? And we saw some results. Amir showed those results for the inferencing, this ML-PERF. And I think that is gaining a lot of traction. In fact, in some of the conferences, you will see dedicated workshops. I believe it is HPCA or HPCA. There is a dedicated workshop every year on this ML4. But to get the numbers using ML4 sometimes is very time consuming. So you have to see, but of course they have given some different model sizes and all. So keep an eye on that. And then, of course, this whole field of AI, as you know, there is a lot of discussion going on open source versus closed source, whether the models are open, how you can do like a closed source, but then with the closed source, you have some APIs, whether you can use. So this is where I think OpenAI started a few years back, and a lot of actions are happening with the DALI, which is like a more like a creates realistic images. Of course, ChatGPT has come. Um, there has been also some of the work called Onyx format because as the models are or the frameworks are changing over the years, systems are changing. Let's say you had already trained your model using one kind of a framework, let's say TensorFlow. Now, of course, that may not be there available on some of the systems, but it has moved to PyTorch. How exactly you can again retrain? So like this, there is also some work taking place, kind of providing this kind of converters. Okay, so we just want to give a little bit of these ideas, saying these are very cross-cutting themes. We didn't go into details, but when we are seeing the large adoption of deep learning, machine learning, training, inference, becoming important in the field of AI. So gradually we'll see more and more such things will come. Of course, I also indicated about ethics. Those are entirely different things. So we didn't bring it here because we are not experts in that area, but that is also very important. And a lot of researchers are working ethics, bias, all those things are also very important for any of these solutions to be practical. So with this, let me formally conclude. Um, Thanks for attending. What we saw like in the last 2 hours, 40 minutes or so, we started with a very high level perspective of where this field is, what are the kind of applications people are thinking, and we see there is an exponential growth in this machine learning, deep learning, data science frameworks. We started with a very high level overview of the issues, challenges, and opportunities, and gradually we went inside, like starting from 100,000 feet level to even 10,000, 5,000, and we were able to run actually as a kind of a live experiments and show the demos how things work on various CPUs and DPUs. Sorry, we couldn't actually give you a lot of accounts and all because the time is a little bit very short. But as I indicated, we have this tutorial at SC, and we also offer this tutorial at other places. With a little bit more time, we'll be very happy to work with you. Really try to do hands-on. We have done that in past. We have GPU clusters. We create accounts so that you can actually feel yourself and then you run these things and learn. But due to the limited time, we're not able to do that today. But in general, you can see like this field is very unique and a lot of actions are taking place. There is a lot of potential. We'd like to thank all our sponsors. But more importantly, these are all my heroes. So what we saw here, like in the last 2.5 hours, uh, we focused on DL, but the underlying is like the communication, runtime, MPI. So as we saw in one of the project, I'm happy we are running it for 23 years. So what you are seeing here is actually a work of more than like 100 people. Here you will see the students, staff, and all. Many of them have graduated and leading very large organizations, large projects at many different companies, Facebook, Microsoft, all the national labs. So with this, so I would like to really thank all of them because everybody, the student staff come, they build on the top of each other, and then we are able to bring you the complete solution for a good understanding. So with this, these are our pointers. If you have any last minute questions, we'll be very happy to take it. Otherwise, please send us an email, and also we'll be happy to answer questions. Okay. So with that, I think. Was there a question? There is a question might be on the chat. I don't know. Okay, so just the feedback. So I hope that gives you a perspective. Once again, we can't like teach you everything in 2 hours, 45 minutes. That is too short. But hope this gives you a perspective so that next time you can take a look at the paper or a trend, then you will be able to correlate what those researchers are working on or what products they are working on. And so with this, we'll be happy to say goodbye. And it has been a long day. I know I saw some of you in the morning tutorial. You have been sitting for the entire day. And also some of you might be attending also the conference. So it's a long 3 days conference. Thank you.
Wonderful. Thank you all very much. That was a great tutorial. We will
Thank you.
leave the Slack channel open, so if anyone wants to refer back to that, it will stay around. And everyone, it was a great tutorial day, and have a great rest of your evening.
Thank you. Bye.
Bye.